Hi, everyone. Today is our lecture for February 1st, 2018, and the topic of the lecture today is leveling. Now, in lab on Tuesday, we used a level to establish differences in elevation between two different points, and we also looked at the functioning of three different levels and came to understand that one of those levels is not working properly. So, building on that information, we're going to talk about some terminology involved in leveling. And this material is in Chapter 4 for the engineering surveyors in the Wolf and Gilani book, and it's also in Chapter 4 in the practical surveying book uh, for the practical surveyors. So, in either case, please refer to Chapter 4 while we're working through this material. Somebody may have told you a while ago that the Earth is round. And the Earth is not actually round, but it is also not actually flat. The shape of the Earth is called an oblate spheroid, which means it's a slightly flattened shape that is similar to a sphere. There are also local differences in elevations. There's mountains, creeks, depressions, grades of different sort. So when we talk about a level and we talk about the idea of a horizontal line or a level line, in everyday usage we would probably think of these two things as being the same. But here on this diagram, from the point of view of a level, we actually have a difference. So we're going to talk about this just a little bit. A vertical line is what we actually establish when we level the level, when we put it on the tripod and adjust the thumb screws in order to put the leveling bubble in the correct position, not only in an axis but on the other axis as well, so that we establish a level plane. And so if you look at this picture, the first thing that you'll see is that we talk about two different things. We talk about a horizontal line, which is straight, and we actually determine that because it's perpendicular to a vertical line. But the curvature of the Earth creates a situation where a vertical line struck at a different location would result in a different horizontal line. So instead of talking about horizontal lines, we also talk about, or I should say in addition to talking about horizontal lines, we also talk about level surfaces and level lines. So a level line is actually a curved two-dimensional geometric shape, and a level surface is the three-dimensional projection. So if you were to create a level surface on the Earth, you would actually have something that was very close to being a sphere, or in theory it would actually be a sphere. Now, the words here when we talk about a vertical datum and the geoid, a geoid is the mathematical representation of the oblate spheroid of the Earth. And when we refer to the idea of geoid, we're really talking about the idea that we have a situation where the surface of the Earth does not actually correspond exactly to a geometrical or mathematically determined shape. So a geoid is the hypothetical shape of the Earth that coincides with mean sea level and its imaginary extension over land. So this brings us to this idea of a vertical datum. The vertical datum that we use most often is mean sea level, or MSL. The word mean refers to the idea that it's an average. If any of you have spent any time at the ocean, you know that that sea level varies during the day and during the month and at different times of the year. Sea level rises and falls with the tide, and also rises and falls with at different times of the year based on, well, a bunch of different stuff. So when we say that the city of Powell, Wyoming, for example, is at an elevation of, I'm going to tell you just a minute here what the data tells us. Tells us that Powell, Wyoming, or that's Lake Powell, sorry, let's get this. Lake Powell, let's just talk about Lake Powell. Lake Powell is the lake that is impounded behind a dam at in Page, Wyoming, or Page, Wyoming, Page, Arizona. Sorry, I shouldn't look at two screens at the same time. It's impounded behind the dam at Page, Arizona, and the elevation of Lake Powell is 3,652 feet. What that really means is that whatever this mean sea level is, Lake Powell exists 3,652 feet above it. But Glen Canyon Dam, the dam that impounds Lake Powell, is the level of the lake can go up and down, but it's never based on a datum that goes up and down. So in other words, sea level rises and falls, tides go in and out, but there is one elevation that establishes mean sea level for the entire world. And it's not really where the level of the seas are at any given point, because that number varies not only from sea to sea, but also from time to time. So the mean, or the average, of a whole bunch of these levels has been established as the vertical datum, or geoid, and that is called 0 feet mean sea level. And it's somewhere in the vicinity of sea level. So when you read something like the city of New Orleans is 8 feet below sea level, it really doesn't mean that there's a wall of water 8 feet tall off to the south of New Orleans. It just means that whatever this datum is, New Orleans is below it. And those numbers don't change. The elevation of a city or the elevation of a place does not change based on time or based on the fact that that sea level rises or falls. And that's actually the meaning of the word datum. Datum just means something that you refer to. So the idea of mean sea level was created by the National Oceanography and Atmospheric Administration, or NOAA, and it was just created by a series of buoys that are put out into the ocean and into seas to establish how much it varies, and then a number was arrived at, and that fixed starting point is the 0 on our scale of operation. So here in Powell, Wyoming, our elevation is stated as being 4,393 feet, which means that we are approximately not quite a mile above mean sea level. Just for interest, Laramie, Wyoming is at an elevation of 7,165 feet. And if you're at an elevation of about 10,000 feet, you actually need to have oxygen administered. So, last point of general information, the highest incorporated town in the United States is Leadville, Colorado, and the elevation in Leadville is 10,152 feet. There are places in Chile that are higher than that. In the Andes Mountains, there are towns that are at quite a bit higher than that. So the elevations can be quite high. So the highest mountain in Chile is the Torres del Paine, and it's at about 9,462 feet, but some cities are much higher. So there are just some different ideas in terms of mean sea level. So the Earth is not flat, is my basic meaning, and it's closer to being a sphere than it is to being flat, but it's also not a sphere. So when we continue this, when we talk about setting up a level, if we set up a level here at A and we sighted to point D into point H, this is something similar to what we did in class on Tuesday. We did a forward sight, and a backward sight. And what we're doing is we're looking for the difference in elevation between those 2 points, in this case between H and D. This is complicated by the fact that the horizontal line that we shoot is not actually equivalent to the level line, which involves the curvature of the Earth. And there's also a property called refraction that any piece of optical equipment, such as our level, is subjected to. When you look at something through any sort of a medium, like air, the image will appear to be above or below what you're looking at. And in the case of the atmospheric correction, you can see that the difference between the horizontal line and the level line is actually greater than the difference between the level line and the line of sight. So the refraction actually reduces the error between where you're sighting and where you're looking, what you're looking for and where you're looking for it, I guess would be the best way to put it. So these are just things to keep in mind. Now for engineering surveyors, we will learn how to make this correction, and it's relatively simple. As you can see, it gets progressively larger the longer the sight that you take. The other thing that you may realize is that if we're looking for a difference between two elevations, H and D, if we balance the backside and the foresight, in other words, if they're relatively the same length, then the curvature and refraction errors are going to be very similar. So we're not really going to have to correct for it. So the first line of defense in correcting for curvature and refraction is just to have a backside, a forward sight, and a backside that are approximately the same distance from the machine. Does not have to be at an angle of 180 degrees, because if you think about it, surface of the Earth is a three-dimensional surface. So if you go 180 degrees due north, excuse me, 180 feet due north, and you just turn maybe 75 degrees so that you're going not quite due east, even though your two lines look like this, as long as they're the same length, the curvature and refraction is going to balance itself out. So this is just talking a little bit more about refraction, getting into that idea that there's going to be an if you have light rays going through the atmosphere of the Earth, that you will have a difference in the apparent position of a particular object to the actual position of that object, so that angles actually have to be corrected as well. All right, now in our discussion we talked a little bit about the way that our automatic levels work. And automatic levels, what they really are is a piece of optical equipment. And what they attempt to do is to use a lens in order to keep a level line. But compensators are added to electrical levels because what really happens is some of that optical equipment has to be suspended in order to compensate, to reuse that word, for some of the variations in movement. And we're not going to really talk very much about that in this class. However, I put a website here if you're interested in reading a little bit more. It won't be tested on, but it's something that we'll just sort of briefly explain to you how levels work and how the compensators help them compensate for some of the differences in sighting. All right, so this is a picture showing how we do a differential level. And here are some terminologies that we're going to be using in the next two labs, which will involve working with an automatic level. First of all, this symbol represents the tripod and the level instrument set up on top of the tripod. The term HI stands for the height of the instrument. Very often, this is not terribly important. If you're looking for the difference in elevation from here to here, then you really don't need to know the height of the instrument. As long as you just can take a reading here and here, you can take the difference between them to get the difference in elevation. That's why it's called differential leveling. So if we have, we're taking an elevation difference between a rock and some other random spot. When you have something that's fairly fixed in location, we refer to that as a benchmark. So this rock with the prefix BM, BM just stands for benchmark, indicates that the rock is fairly permanent. Determining permanency is a relative term. A lot of times for permanent objects that you want to refer back to in order to have something fixed, you can use fire hydrants, you can use extruded concrete, fence posts embedded in concrete, that sort of thing. You wouldn't necessarily want to use a mound of dirt because a mound of dirt can be moved very easily. Now, I say this recognizing that the difference between permanence and temporary are vague. It's sort of a spectrum. But if it's basically permanent for the purposes of your survey, it's referred to as a BM or benchmark. Now, something like this, the X marks a spot that is not a benchmark, but is rather just a temporary point. And so that can be indicated by TP, which just stands for temporary point. So why would you set a temporary point here? Well, maybe there's another benchmark up here, and you want to know the difference between this benchmark and that benchmark. But you can't really sight to the whole thing without having a very tall tripod and a very tall rod. So you can set up a temporary point in the middle, sight from here to here, leave the rod here, move the tripod to, for example, here, sight here and to the top. Then you know the elevation difference between here and here, the elevation difference between here and here. You can add those two together and get the elevation difference between here and here. And that's referred to as, once again, differential leveling. Now there are other methods of leveling. One is barometric leveling, and if any of you have ever flown in personal aircraft, the object that tells you what your altitude is called an altimeter, and they are generally speaking barometric, or they measure pressure. As you increase in elevation, the atmospheric pressure decreases, and as you go down in elevation, the atmospheric pressure increases. You can use that idea plus a standardization from the Weather Service in order to determine your elevation, which is extremely important when it comes to avoiding objects and landing appropriately at the airport. All right, this is another way to level, and once again we'll talk about this a little bit in future classes, but this is referred to as trigonometric leveling. You may not have a level but an instrument that measures also either vertical angles, which are alpha, or zenith angles, which are indicated by the Z in the curve here. And using trigonometry, you can determine the horizontal distance h based on a slope distance and an angle. And we can talk about that a little bit later on. For now, suffice it to say that the engineering surveyors will do these math calculations and the practical surveyors will not. So trig leveling is very important. You can also do it if you don't really have a level surface. This is a little beyond the scope of this class, so we're not going to go into it, but just so that you know, you can strike level lines and horizontal lines, take into account angles and the Earth's curvature, and of course refraction, and make some calculations to develop a horizontal distance. Now the other thing, I'm going back to slide number 8 here. When you look at maps are almost always laid out in horizontal distances, not slope distances. So slope distance is the distance along the path of wherever you're measuring from and to. The horizontal distance is the distance that is just in the horizontal direction, and the other factor, the other leg of this triangle, quite literally, is the vertical distance. So you have a horizontal distance, a vertical distance, and a slope distance. They're all intimately related through either the angle alpha, the vertical angle, or z, the zenith angle. So here's a picture of a little level, and we've already done this in class. I think it's much easier to do this when you're working with a piece of equipment rather than looking at the piece of equipment. So nothing here should strike you as unusual or something that you have not seen before. And here's a different kind of a level. Once again, same sorts of parts. Not every level that you look at is going to be the same, but they all sort of function the same way. So with a basic understanding of how they work, you can use those basic principles to determine exactly what you can measure and how to measure with that piece of equipment. This is, well, at one point it was modern, but this is sort of a lower tech piece of equipment. This is called a total station, and we will work with one later on. We actually have two in our classroom. So I have one that's circa 1995 and one that is just a couple of years old. So we'll get to use both of those. Here are old friends, the Philadelphia rods. We've talked about how these work, starting at a smaller number, working forward, working upward to a larger number. Smaller readings on the rod indicate higher elevation. The difference in readings on the rod, if you leave the machine stationary, will give you the difference in elevation between those 2 points. All right, and this is just something, this is what happens if you don't level your level. Okay, so we definitely want to make sure that we have our equipment leveled and are ready to proceed with that. All right, so the assignment for practical surveyors is to read chapter 4 in your textbook. The title of chapter 4 is Measuring Vertical Distance. It begins on page 73 and it continues through page 90. And on page 90, 91, and 92, there are some review questions. So I would like you to go through these review questions. 21 and 22 are going to be a little involved. We may need to do them in class, but I want you to take a look at them and see if you can ascertain from my lecture today and from the reading in the book what those values would be. This is also going to look very much like the lab that we're going to do in a couple of weeks. We're going to have to keep our note form in this manner in order to facilitate the calculations. So for practical surveyors, I would like you to do all of the review questions, that's 1 through 25, on pages 90 through 92. And for the engineering surveyors, once again, after you view this lecture, I would like you to read chapter 4 in your book. And it goes into a little bit more detail about different types of leveling, and also talks a little bit about vernier scales, which we will talk about, but not quite at this time. There are review problems in the back, problems 4.1 through 4.35, and I would like you to skip a few of these problems. So I would like you to skip problem 4.5 and 4.4 is a pretty good problem. Let's just skip 4.5 at this time. 4.4, if you want to use Excel or something for that, something in a spreadsheet, it will go much, much quicker if you're familiar with Excel. The other thing is, I do want to alert you to the fact that I've referred to back sites and forward sites. Your authors in the textbook for elementary surveying sometimes refer to these as plus sites and minus sites. But a minus site is what I'm referring to as a forward site, and a plus site is what I'm referring to as a back site. So they refer to that because those are the signs in a particular kind of way that you either add or subtract from something else. And you'll see how that works in the textbook, but they're exactly the same thing. So thank you for your attention. And engineering surveyors, you will skip problem 4.5, and I think that's it. Do the other problems 1 through 35. And practical surveyors, give a go to all the problems, recognizing that 2 of them are going to be a little bit more involved. We may need to spend some time on them in class. And this assignment will be due 1 week after the last assignment, so I'm going to post it up to Moodle. Thanks. Have a great day.